Hello everyone, and welcome to this video on the Gram-Schmidt process for orthogonalization and orthonormalization. Some fancy words. So in this video, I'm going to start off in Euclidean vector spaces, R2, R3, so we can actually visualize things. Under the dot product as well, the inner product for these spaces, I'll start off with the dot product. And we'll what this process is, this Gram-Schmidt process for orthogonalization and orthonormalization, is if you have a vector space and you know a basis for that vector space, can you then construct an orthogonal basis to that vector space? And furthermore, can you construct an orthonormal basis for the vector space? Right? And as you've seen in previous videos, again, if you've been watching mine, when we have an orthogonal basis for a space or an orthonormal basis for a space, those are very nice bases because vectors, when you write the coordinates of vectors relative to an orthogonal basis or relative to an orthonormal basis, the coordinates are actually very easy to find. So we like having an orthogonal basis for a space, or especially an orthonormal basis, right, where every vector is a unit vector, has a norm of 1. All right, so let's get into this. So we're talking, Gram-Schmidt orthogonalization or orthonormalization, or just the Gram-Schmidt process. So I'm going to start off, as I mentioned earlier, I'm going to start off in the inner product space R2, right, two-dimensional Euclidean space, under the standard inner product. Right, so that's where the inner product of two vectors is the dot product. Standard inner product, Euclidean inner product. So suppose, say we're given a basis for R2 that's, not orthogonal or not orthonormal, because if it was orthogonal or orthonormal, an orthonormal basis already, then I wouldn't have to go through this process. So given a basis for R2, can we construct an orthonormal basis for R2, from that original basis? Okay, so here's how this is going to go. And again, I'm doing R2 and R3 first because we can do some visualizations. I can draw pictures. But the way this procedure is going for R2 and R3 will be generalized to any inner product space. So suppose I have a basis B. It's a set of, remember, a dimension of R2 is 2, so any basis is going to have two vectors in it. So say B has the vectors u1 and u2 in it, and they are a basis for R2, right? So they're independent and span R2. So first step is I'm going to take this basis here and use these vectors to help me construct an orthogonal basis for R2. And this orthogonal basis I'll call B prime, right? Because it's not B, but it's, I'm using B to help me get it. So I'll call this B prime with vectors v1 and v2 this orthogonal basis for R2. So how do I find these vectors v1 and v2? So I've got a little drawing here, and we're in R2, so just vectors on the plane. So say u1 is this blue vector here pointing to the right, and u2 from basis B is this red vector pointing up like this. Notice I've set them up so that they're not orthogonal already under the dot product. They don't form a 90-degree angle, because if they were, I wouldn't bother doing this process. Now in my last video, again, hopefully you've been following, watching, paying attention, I talked about the projection of one vector onto another. Alright, so if I just pick one of these, say u1, say I keep u1 the way it is, I pick that vector to be one of my basis vectors. Let's say u1 is v1. All right, so I'm gonna have u1 be the v1. That simple. Then I want to find a vector that's orthogonal to this vector, right? That meets it at a 90-degree angle, because we're talking about dot product here for the inner product. So 90-degree angles. If you were to draw the projection of vector u2 onto vector u1, right, that's just take the end of u2, draw a little perpendicular orthogonal segment to u1, then the vector here, this green vector I have below, just this short one, that's the projection vector, the projection of u2 onto u1, the orthogonal projection. And then that segment I drew, that segment, if I drew a vector from, say, the end of the projection vector to the end of u2, I draw that vector going up. That vector is orthogonal, right, forms a 90-degree angle with u1. That vector is simply u2, right, u2 minus the projection vector. So u2 minus the projection of u2 onto u1, or u2 onto v1, right? Remember, because I called u1 v1 as well. Right. And there you have it. All right, these two vectors are going to form an orthogonal basis for R2. There's two of them, and they would be orthogonal. Their inner product, their dot product, would be 0. And just recall over here, I got a little, again, this is from my last video on projecting, the orthogonal projection of one vector onto another vector. The projection of a vector u onto a vector v is a scalar multiple of v. Right? If you're whatever vector you're projecting onto, the resultant vector would be a scalar multiple of v, right? Because you'll be in the span of v, or on the line containing v. So the projection of u onto v is the inner product of u with v divided by the inner product of v with v, or the norm of v squared, then times v. All right, so let's keep that in mind for the next page. So, but like I said, I have found, starting off with u1 and u2, I have found two vectors that are orthogonal, that in this case perpendicular, that would form a basis for R2. Right, so I wrote the process here. Now this is just the process for R2. It's going to be a little more involved for higher dimensional spaces, as you'll see with R3 coming up. So like I said, step 1 in the process, I'm going to let this v1 in my orthogonal basis just be u1, just the first vector from the original basis I had. So I let v1 be u1. And then this vector here, the u2 minus the projection of u2 onto v1, or u1, that vector was orthogonal to it. So I'll let v2 from this orthogonal basis I'm trying to create be equal to u2, right, the second vector from my original basis, minus the projection of that u2 onto v1. Again, or u1, but I tried to write v1 here. I accidentally wrote u1, but they're the same, right? u1 and v1. And these two will be orthogonal, this v1 and v2. And we can check, right? I'll just do it for this one. I just wrote it out for this example here. We could check that they're orthogonal, this, u1 and u2 minus the projection of u2 onto v1 or u1, by taking their inner product. So the inner product of v1 with v2 is, again, v1 is u1, v2 is u2 minus the projection of u2 onto v1 or u1, right? v1 and u1 are the same thing. So notice I have all the u1s here. Well, remember the inner product, if it's a well-defined inner product as the dot product is, there's additivity and homogeneity properties. So this inner product would be equal to the inner product of u1 with u2 minus this scalar pulled out, right? This is a scalar, this division of the inner products here, the inner product of u2 with u1 divided by the inner product of u1 with u1, then times the inner product of u1 with u1, right? Using the additivity and homogeneity properties. You see in the second term, the inner product of u1 with u1 is in the numerator and denominator, so those would cancel. And I'm left with the inner product of u1 with u2 minus the inner product of u2 with u1. But remember the symmetry property or commutative property for inner products. These are the same, so this is 0. This would be 0. So the way I have set up v1 and v2, they are orthogonal. Right? Remember the little perpendicular signal for orthogonal. Right? So v1 and v2 are going to be orthogonal if I define them the way I did up here. So that b prime, that v1 equals u1 and v2 equals u2 minus the projection of u2 onto v1, this is going to be an orthogonal basis for R2. Right, there are two of them. They're going to be independent. Remember, and it's an orthogonal set. Remember, any orthogonal set of non-zero vectors will be independent. So we have a basis. All right, and then as you've probably seen in earlier videos of mine related to this, when the word orthogonal shows up, the word orthonormal isn't far behind. And if you have a set of vectors that's orthogonal, like b prime is here, to construct an orthonormal basis, an orthonormal set that's a basis for R2, say b double prime equals w1 and w2, just normalize the vectors from your orthogonal basis. Right, so that's the only step here. Normalize the vectors from b prime. Remember, to normalize means to turn it into a unit vector, right? A vector with a norm of 1. And that's simply by taking the vectors in the orthogonal set, right, in b prime, this v1 and v2, and dividing by their norms. So w1 in this orthonormal set will be just v1 divided by the norm of v1. And w2 in the orthonormal set, the orthonormal basis for R2, will be v2 divided by the norm of v2. And just remember how to find the norm using an inner product, right? The norm of a vector in an inner product space was the square root of the inner product of that vector with itself. All right, so this set here with these two vectors would be an orthonormal basis for R2. All right, in this process I just described, where I let v1 be the first basis vector, v2 be the second basis vector minus its projection onto v1, and then normalizing them to get an orthonormal basis. This process is called the Gram-Schmidt process, all right, or Gram-Schmidt orthonormalization process, or the Gram-Schmidt orthogonalization process. All right, so let's do an example. All right. So, and I'm just in R2 right now. We'll go to other spaces later. So my first example is, apply the Gram-Schmidt process to transform the given basis of the given inner product space into an orthonormal basis. I think I'm going to go through these steps of first transforming it into an orthogonal basis, and then just normalizing the vectors to make an orthonormal basis. All right. So the inner product space, as I mentioned in the previous pages, I'm going to start with is R2 with the inner product being the dot product, right? The standard inner product, or the Euclidean inner product. All right, so here's a basis for R2. Right? These two vectors are independent, right? They form every vector and they span R2. Every vector in R2 can be written as a linear combination of them. So say U1 is the vector 4, negative 3, and U2 is the vector 3, 2. Okay. Now they do form a basis, but notice they're not, this is not an orthogonal basis. If I perform the inner product, if I did the dot product with u1 and u2 here, these two vectors, I'd get 6, right? 12 minus 6, I'd get 6, not 0. So this is, not an orthogonal basis, and if I were you, I would check that first, because if you're given an orthogonal basis, you don't have to do the Gram-Schmidt process, because it's already orthogonal. So I think the first thing I would do is ask myself, is the basis that they gave me an orthogonal basis? That's ORTH, sorry. So I take the inner product of u1 with u2, or the only pair of vectors in there, and like I said earlier, I'd get 6, which is not 0. So the answer is no. Right? So this is not an orthogonal basis already, meaning I in order to transform it into an orthogonal basis, I should now start the Gram-Schmidt process. All right, so here it is. Right, so I'm going to write out this is so that now we start the Gram-Schmidt process. Right, so like I was saying, the first step, I know this is the second step technically, but no, I'll call it I instead of 1. Right, what we're trying to find, right, first I'm going to find, let's find an orthogonal basis to R2, not orthonormal yet, but let's find an orthogonal basis, and again I'm going to call it B prime, because it's coming from B, but it's not equal to B, right? It's different, with vectors v1 and v2, right, which are different than u1 and u2. Now v1 is just u1. Just pick the first vector. Let that be in b prime. Right? So 1, I'm going to just let v1 be equal to u1. Right, so v1 is simply going to be the vector 4, negative 3. Simple as that. Right. Then the second vector, v2, is I take the second vector in my basis, right, u2, and I subtract the projection of u2 onto the earlier vector I found, onto v1. The projection of u2 onto v1, and since v1 was u1, you could also call that u1. But again, using the formula for a projection, this is u2 minus, and then the projection of u2 onto v1 would be the inner product of u2 with v1 divided by the inner product of v1 with v1 times v1. All right, let's fill in all these numbers. Let's see what these are. Okay, so what is u2? u2 is that, the second vector from my original basis, the vector 3, 2, minus, and then this projection here, I'm going to do these inner products. So what's the inner product of u2 with v1? So what's the inner product of 3, 2 with v1 was 4, negative 3? Well, that's 3 times 4, 2 times negative 3 is negative 6. That's 12 plus negative 6. That's 6. We already saw that. So 6 in the numerator. Right, that's u2, the inner product of u2 with v1, the dot product. And then what's the inner product of v1 with itself? So that'd be 4 squared plus negative 3 squared, right? v1 with itself, dot product. 16 plus 9 is 25. So I'm getting minus 6/25 times vector v1, right, times 4, negative 3. Right. Now let's put these together. So this is 3, 2 and minus, and multiplying these by, say, that's 24 25ths, and negative 18 25ths. All right, putting these together will give me what I'm going to call V2. Right. So that's 75 25ths minus 24 25ths. Maybe 51 25ths. All right, and then this is 50 25ths, the number 2, right? 50 25ths minus negative 18 25ths. So that'd be plus 18. So 50 plus 18, that's 68 25ths. And there's V2. All right. Okay, which, if you'd like, I'm noticing that both of these have 1/25th in common, so I'll pull that out. 1/25th times the vector 51 68. Right. So there we have it. Here's our an orthogonal basis coming from this Gram-Schmidt process. So B prime equals, again, V1 and V2, the vector 4, negative 3. Where, again, V1 was just U1. And V2 is this 51 25ths, 68 25ths. Right. This is an orthogonal basis. Right, this is an orthogonal basis for R2. Okay. Now, you could also, there's nothing wrong with this, if you don't like the fractions, if two vectors are orthogonal, right, their inner product is 0, I mean, you can multiply each of these by any scalar you wanted, right? Because if two vectors are orthogonal, any scalar multiples of those two vectors will also be orthogonal. So if you don't like the fractions here, I just multiply this second one by 25, right? Or we could say that, B prime equals 4, negative 3, and then multiplying that second one by 25 to get rid of the fractions, 51 68. This is also an orthogonal basis. And something else I'm seeing is, I'll say, is also an orthogonal basis for R2. But something else I'm also noticing is that 51 and 68 are actually both multiples of 17. So if I wanted to, right, again, if two vectors are orthogonal, you can multiply those vectors by any scalars you want, and as long as you don't multiply by 0. I mean, 0 would still work, but then you wouldn't have an independent set. But I'll multiply this one by 1/17 now, and I didn't see that earlier, but I'm seeing it now. I could say B prime equals 4, negative 3, and then 51 is 3 times 17, and 68 is 4 times 17. So if I multiply by 1/17, that'll be 3 4. And this is also an orthogonal basis. All right, now the one that came from the Gram-Schmidt process was this one. Okay, the one that came from the Gram-Schmidt process was this one. But all I did after that was simplified by scalar multiplication. Because like I said earlier, if a set of vectors is orthogonal, you could multiply any of those vectors by any scalar, and it would still be an orthogonal set, right, due to properties of the inner product. Okay, and you can double check me. Right? Let's see if that's true. Let's do the dot product of these two, the inner product of these two. 4 times 51 is 204, so I have 204 25ths. Negative 3 times 68 is negative 204. So I have 204 25ths minus 204 25ths. That's 0. And then down here, just 204 minus 204, 0. 12 minus 12, 0. So like I said, if you have an orthogonal set, you can simplify things if you wish through a scalar multiplication. Just multiply vectors by scalars to make them nicer looking, and you'll still have an orthogonal set. Okay, but if you're ever asked on a test or something, a lot of people, when they examine you on this stuff, tend to want to have you come out with the same answers, so it's easier to check. So if they said, hey, use the Gram-Schmidt process to find an orthogonal basis to R2 here, this is what I'd come back with. Right? And these are totally fine as well. Right? In fact, I'm going to use this one to find an orthonormal basis, because you'll see either way I do it, whether I use this one or this one, the orthonormal basis that comes of it will be exactly the same. All right, so there's an orthogonal basis. Now we'll find an orthonormal basis. All right, so like I said, I'm going to use the nice one here. I'm going to use this. I'm going to use this one with the vectors 4, negative 3, and 3, negative 4. Right? I'm going to use this and normalize. So let's call this V1 and V2 now. So now just normalize. So what's the norm of this vector? It's just 5, right, under the dot product. 4 squared, 4 squared plus 9, negative 3 squared, 16 plus 9 is 25, then the square root of that. Same thing for the norm of V2 here, right, 3 squared plus 4 squared, that's all, and the square root, that's also 5. Now the only difference between this one and this one with the 25ths is, the norm of this vector. This vector 3, 4, if I multiplied it by 17 25ths, I'd get that vector. So the norm of this vector would be 17 25ths times 5, or just 17 fifths. And then I'd multiply by 5 17ths and get our unit vector. And we'd end up with the same unit vector, right? Because when you're looking at a vector in any direction, in one direction, there's only one unit vector that points in that same direction, right? So you're always going to end up with the same result when you normalize. So then B double prime equals 1/5 times the vector 4, negative 3, and 1/5 times the vector 3, 4. All right, or if you'd like to actually put the scalar inside, this would be the vectors 4/5, negative 3/5, and the vector 3/5, 4/5. This would be an orthonormal. Right, this is an orthonormal basis. For R2, right? It's orthogonal, right? Their inner product is 0, and they're both unit vectors, and you can double check that. The norm of this would be 1, the norm of this would be 1. Wonderful. Wonderful. Okay. So let's see a picture of this. I know there's a lot of numbers here. All right. Let's look at a picture of this. What's happening? All right, so back to my first two vectors were 4, -3, and 3, 2. So I'm going to go, I got the geogebra.org site up with some vectors marked, right? So you see U1 in red is the vector 4, -3. U2 in blue is the vector 3, 2 on the regular coordinate plane here, R2. And you see they point in different directions, right? So they'd form a basis for R2, but not orthogonal, right? These don't look like they're forming a 90-degree angle. All right. So remember, to make the orthogonal basis, I kept U1, right? So I kept 4, 3, and then U2. I called that V1, right? I called U1 V1, and then U2 was, or I'm sorry, V2 was U2 minus the projection of U2 onto V1, which I have back here, right? So again, I let V1 be U1, 4, -3, so I'll keep that. And then V2, right, I have it here still, was U2 minus the projection of U2 onto V1, or this formula, which after finding it was this vector here, the 1/25 times 5168. Which I simplified by multiplying by scalars to the vector, 3, 4, but I'll stick to the one I got from the process. Right? So let's go back, and I'll enter that vector. So I'm going to call this V2, because again, U1 is the same as V1. V2 is 1/25 times the vector 5168. Right, and look at that. Look at that black vector show up, V2. And let me get rid of U2 now. See the orthogonality here, right? Remember, we're talking dot products, so orthogonal is perpendicular, forming a 90-degree angle. See if I zoom in, maybe you can tell a little more easily. But see V2 and V1, it says U1, but it's now V1. These form a 90-degree angle. They form an orthogonal basis for R2. Alright, and then I just normalized these. Alright, so if you multiply the first vector by 1/5, right, so I'm going to call this, let's say we call this W1. Right, remember I multiplied that by 1/5, 1/5 times U1. And you see that W1 show up on U1 there. That's in the same direction, but it's just a unit ln. And then W2 will be equal to, now I left it as 1/25 times 5168. Right, the norm of this vector would be 17/25 times 5, so 17/5. So I'd multiply that by the reciprocal of 5/17. Right, 5/17 times V2 there. And you see W2 showing up. All right, let me get rid of V2, but it's on the same line as V2, see? But only a unit ln. And there, W1 equals, look at this, see, 0.8, -0.6, that's 4/5, -3/5. W2, 0.6, 0.8, that's 3/5, 4/5, exactly the same two vectors I got earlier, right, after normalizing, right, 4/5, that's 0.8, -0.6, 0.6, 0.8. And you see this is an orthonormal basis, right? They both form they form a 90-degree angle. It's dot product here. They form a 90-degree angle, and they're both 1 unit ln. So really what this is here is kind of a rotation of the standard basis vectors for R2. All right, remember standard basis was 1, 0, 0, 1. Those are orthonormal, right? They form a 90-degree angle and are 1 unit ln. This is just that kind of rotated a bit, clockwise. Great, and hopefully it's obvious, so hopefully we can see that we have formed an orthonormal basis for R2 here. All right. So yeah, it's a bit extensive, right? But that was only for two vectors. Right? This was the procedure here, right? Now this concept of subtracting projections is just going to keep playing out. It's just going to keep extending as we get more and more vectors. All right, so I'm going to show you the same procedure in R3 under the dot product, and then we'll generalize it to any inner product space. All right, so here we are now in R3. Right, in R3 with the inner product being the dot product. Right, just so orthogonal means perpendicular, right, forming 90-degree angles. So suppose we have a basis for R3, right, which would have three vectors, three independent vectors. Say U1, U2, and U3. And I want to construct an orthogonal basis for R3. Now again, I would check, is this orthogonal? Because if this is already orthogonal or orthonormal even, then you don't need to go through the procedure. You don't need to go through Gram-Schmidt. But if it's not orthogonal, right, then we would have to do something. All right, so let's construct an orthogonal basis for R3. Say I'll call it B prime is vectors V1, V2, and V3. So just like the last step, the last procedure with R2, this V1 is going to be the first vector from my basis. So I'm going to let V1 equal U1. And here I've got a drawing. Now it's kind of hard to tell, but these are supposed to be in 3 dimensions. Okay, so let's say U1 and U2, right, they span a plane, and then U3 is off that plane. All right, so and what I'm trying, so what I want to do is we're going to eventually project U3 onto the plane. So like whatever, this is coming right, this is over it and is on the plane spanned by U1 and U2, and I want to project U3 onto this plane, right, to form a 90-degree angle here, straight down. Okay, so hopefully the shading and the little segment there made this a little more obvious that I'm talking about 3 dimensions. Alright, so here's U1 and U2. Now I start off the same way as I did with R2, with 2 vectors. Right? Let's look at U1 and U2. Again, I'll just have U1 be the V1. Right? I'll have the first vector in my orthogonal basis be the first vector of my original basis. So U1 is V1. And then I want to find a vector that's orthogonal to this. Well, I can use U2 to do that by finding the projection of U2 onto V1 and then subtracting it from U2. So it starts off exactly the same. I let V1 be U1, and then I let V2 be U2, right, the second basis vector, minus the projection of U2 onto the first vector in this new basis V1, right, which was the same as U1. All right. Now, let me take this to the next page. So again, we got U1, U2 here, but now this time I'm using U1 as V1, and this U2 minus the projection of U2 onto V1 as the other vector V2. All right, now this is a really crappy drawing. I'm going to warn you right now. So you see now I'm using, this is V1, which was U1 before, and this is V2, which is perpendicular to V1, right? And this V2 is the U2 minus the projection of U2 onto V1. And they form a plane, right? So I'm going to draw maybe hopefully a better picture over here. Let's do this. So let's say this is V1, then this is V2, right? And they're perpendicular, right? Now I know it doesn't look like it, but I'll make a little perpendicular symbol here. There we go. Little box, right? They're perpendicular. Maybe stretch this out a bit, right, like that. Now what I want to do is find a third vector that's, perpendicular to this plane, right? Because these two vectors span a plane, and what I would like to do is find a third vector that's perpendicular to them. All right, so here's how this works. So again, my drawing here is kind of crap. I'm going to try to redraw something over here. I take the third basis vector. I take u3 from my original basis, the u3. I'm going to project it onto v1 and project it onto v2. All right, so we get something like this. I'll draw this maybe hopefully a little better over here. So let's say this vector is the projection of u3 onto v1, and say this vector here is the projection of u3 onto v2. That's really cluttered. And those should be perpendicular, right? Those should be orthogonal because they're in line with v1 and in line with v2, and those are already orthogonal. And these two vectors kind of are the sides of a rectangle. You can think of these as the sides of a rectangle at the bottom of a rectangular prism. Right, so let me draw this in here. So there's the projection of u3 on v1 again up here. And here's the projection of u3 on v2 again here. And again, this is supposed to be these are 90-degree angles, all these. So I get this square, or not a square, I get a rectangle at the base. And then u3, right, the tip of u3 is right above the diagonal corner here. If I draw u3 in, so you see, this is why I usually don't like doing three-dimensional drawings. So let's say this is u3. All right, this is u3. And if you set it up right, the tip of u3 should be directly above that corner of the rectangle down here. So if I project it, we're getting this 90-degree angle here. I'm projecting the tip of u3 down to the plane spanned by v1 and v2. In fact, you could think of u3, right, u3 here, as a diagonal of this rectangular prism. If I am terrible at this. All right, if I drew a little rectangular prism there, v3 would be a diagonal from this origin point down here, this lower left corner point, cutting through the box, the rectangular prism, to this upper right corner point, and that should be directly above the plane that's spanned by these projection vectors, or vectors v1 and v2. And this looks just as awful as my first picture. I must apologize. And this diagonal, right, the diagonal of the rectangle at the base, the diagonal of the rectangle at the base is the sum of these projections. That's what I've written over here. The diagonal at the rectangle at the base is the sum of the projections of u3 onto v1 and u3 onto v2. So then the one that's going straight up and down, right, the one that's going straight up to the tip of u3 that I'm looking for, this vector would be v3. And that's going to be just u3 minus the sum of those projections. That's what I've written all up here. And if you distribute the minus sign, you got u3 minus the projection of u3 onto v1 minus the projection of u3 onto v2. So you can see here, again, even if the drawings are crap, you can see that v3, right, the third vector in my orthogonal basis, is the third vector from the original basis, and then I subtract its projections onto the other two I made. Right, I take u3 and subtract the projection of u3 onto v1, and I subtract the projection of u3 onto v2. Right, and if there were four vectors and I was finding v4, if there was a fourth vector, it would be the fourth base. It would be u4 minus the projection of u4 onto v1 minus the projection of u4 onto v2 minus the projection of u4 onto v3, And there we go. I mean, this subtraction of projection vectors just keeps going the more and more vectors you have. All right, and then again, the formulas for projections here involving the inner products. So V3 is U3 minus, the projection of U3 onto V1 minus the projection of U3 onto V2. And double check. If I take the inner product of V3 with V1, the V1 would kind of distribute, right? The additivity property, and some stuff would cancel, and V1 and V2 are orthogonal, so the V1 with V2 term would go away, and you'd get some V1 canceling here, and then you'd basically have the inner product of U3 and V1 minus the inner product of U3 and V1, you'd get 0. So V1 and V3 are orthogonal, and do the same thing for V2 and V3, and you would see that the inner product of V2 and V3 would be 0 as well. This vector, the way it's constructed, is orthogonal to the way V1 and V2 were constructed as well. So we do have an orthogonal basis for V3. All right, so this B prime equals V1, V2, V3 is an orthogonal basis for V3. And then I want an orthonormal basis. I just simply normalize these, right? Take whatever V1, V2, and V3 are and divide them by their norms, and we get W1, W2, W3. We get these three vectors that form an orthonormal basis for R3, all unit vectors that are orthogonal. All right, so yeah, crazy process, I know, right? And that's only with three vectors. But it works. It takes any basis that you start with, and you are able to construct an orthogonal basis to your space, and from there an orthonormal basis to your space. And orthonormal bases are very kind and nice to work with bases. All right, so let's practice this. Let me do an example of this with a basis of vectors from R3, where the inner product is again the dot product. All right. So the space is R3 with the inner product being the dot product, as I said. Pardon me. And here's a basis for R3. The vector 0, 1, 1, 1, 1, 0, 1, 0, 1. And you can double check, verify that these are independent and span R3, right? So we have a basis for R3. Now notice this is not an orthogonal basis. Because again, if it were an orthogonal basis, then you wouldn't have to do the Gram-Schmidt process. Right? For instance, the inner product of U1 and U2 is 1, right? This is dot product, 0 plus 1 plus 0, which is not 0, right? So U1 is not orthogonal to U2. And that's all you need to show that a basis is not orthogonal, is just show that one pair of vectors isn't orthogonal, right? Because remember, for a set to be orthogonal, every pair of vectors has to be orthogonal, or they might say pairwise orthogonal. All right, so it's not an orthogonal basis, so then we can start going through this Gram-Schmidt process to construct an orthogonal basis. All right, so Gram-Schmidt. So first step, easy. Again, I'm trying to construct an orthogonal basis called B prime with vectors V1, V2, and V3. I want this to be an orthogonal basis. Let's write orthogonal next to it. Yeah, orthogonal basis for R3. All right, so first one's easy. I'm going to let V1 be U1, the first vector in the set in the original basis. So V1 is simply the vector 0, 1, 1. Right. Then I start subtracting projections. Right, V2 will be u2, right, the second original basis vector, minus the projection of u2 onto this first vector from my new set, onto v1. And that's it, right? I'm only subtracting the 1. And then when I get to v3, I'll subtract projections onto v1 and v2. And it just keeps going like that from there. Alright, so remember this is u2 minus, and then the projection of a vector onto another vector. So the inner product of u2 with v1 divided by the inner product of v1 with itself times v1. Okay, so what are these? u2 is the vector 1, 1, 0. Right? That's the second vector from my original basis. Minus, what's the inner product, in this case the dot product of u2 with v1? So there's u2, 1, 1, 0. There's v1, 0, 1, 1. Dot product would be 0 plus 1 plus 0. That's 1 in the numerator. And then denominator, what's the inner product of v1 with v1? So v1 is this. That'd be 0 plus 1 plus 1. That's 2. So a half. All right, so I take u2 minus a half of v1. Right, and v1 was again 0, 1, 1. All right, and putting this stuff together, v2 is 1 minus 0, so 1. Then 1 minus a half, which is a half. And then 0 minus a half, so negative half. Okay. I'm going to keep this way. All right, keep this way as 1, 1 half, negative 1 half. It's only after I've created all three vectors that I'll look at scalar multiples to simplify it, but if I want this to work out, I'll keep this as the projection vector the way it is, or u2 minus the projection vector the way it is. All right, so v2 is 1, 1 half, negative 1 half. All right, then for the third vector, the v3, so for v3, I'm going to take u3, okay, the third original basis vector, and subtract its projections onto the first two vectors from my new basis, onto v1 and v2. So minus the projection of u3 onto v1, and then minus the projection of u3 onto v2. All right. Okay, now let's work through these. Again, the formulas would be u3 minus, and then this would be the inner product of u3 with v1 divided by the inner product of v1 with itself times v1 minus, in the projection of u3 onto v2, inner product of u3 with v2 divided by the inner product of v2 with itself times v2. All right, remember what v1 and v2 are. They're up here, 0, 1, 1, and 1, 1 half, negative 1 half. All right, so what is u3? Right, u3 was the vector 1, 0, 1, right, from the original basis. 1, 0, 1. Minus. All right, now the inner product in this case is again the dot product. So what's the dot product of u3 with v1? So 1, 0, 1 with v1, 0, 1, 1. So that'd be 0 times 1, 0, plus 1 times 0, 0 plus 1 times 1 is 1. So the numerator, that's 1. All right, and then again the dot product of v1, the inner product of v1 with itself would just be 0 plus 1 plus 1, or 2. So this is half of, and then v1, right, v1, 0, 1, 1. then minus, and then again the projection of U3 onto V2. Alright, so what's the inner product of U3 with V2? Remember, V2 is this with the 1/2, negative 1/2. Alright. Okay, so now U3 is 101. V2 is 1/2, negative 1/2. So 1 times 1 is 1. 0 times 1/2 is 0. 1 times negative 1/2 is negative 1/2. So I have 1 minus 1/2. That's 1/2 in the numerator. That's just this inner product. All right. Divided by, and then the inner product of V2 with itself. All right, inner product of V2 with itself. That'd be 1 plus 1/4 plus 1/4. So 1 plus 2/4. So 1 1/2. That's 3/2. There's the denominator. Times V2, right? Times the vector 1, 1/2, negative 1/2. All right, so I'll simplify some of this. So we have, U3, 101 minus, half of 0, 1, 1, 0, 1/2, 1/2. And then 1/2 divided by 3/2 would be 1/3. All right, would be 1/3. So I'm putting minus 1/3 in here. Minus, 1/3 times 1 would be 1/3. 1/3 times 1/2 would be 1/6. And then 1/3 times negative 1/2 would be negative 1/6. All right, and then I combine these things, get common denominators and all that. So first component's 1 minus 0 minus 1/3. That's 3/3 minus 1/3 is 2/3. And then second component, 0 minus 1/2 minus 1/6. Well, 1/2 is 3/6. So negative 3/6 minus 1/6 would be negative 4/6, which reduces to negative 2/3. And then 1 minus 1/2 is 1/2, or 3/6, and then minus negative 1/6 would be plus 1/6. So 1 minus 1/2 is 1/2, 3/6, plus 1/6 is 4/6, which is 2/3. So there's V3. Right. So I have my orthogonal basis now for R3. Right. So B prime, right, equals this, V1, V2, V3 through this Gram-Schmidt process is the set of vectors. V1 was just U1, 0, 1, 1. V2 was that vector 1, 1/2, negative 1/2. And V3 is this one that I just found here, 2/3, negative 2/3, and 2/3. All right. This is an orthogonal basis for R3. Under this inner product, right, under the dot product. Remember, the concept of orthogonality depends heavily on how you define the inner product, so pay attention to that. Let's just double check. How about I take V1 with, the dot product of V1 with V2, be 0 plus 1/2 minus 1/2, that's 0, they're orthogonal. How about V1 with V3, that'd be 0 minus 2/3 plus 2/3, they're orthogonal. That'd be 0, they're orthogonal. And then V2 with V3, get 2/3 minus 1/3, and then minus another third. So 2/3 minus a third minus a third, that is 0. So it's pairwise orthogonal, right? This is an orthogonal set and therefore independent, and it's got 3 vectors. So it is a basis, an orthogonal basis for R3. Right. Now, if you'd like to simplify these, go ahead, right? If I'd like to say, hey, I don't like the fractions. Remember, if you have three orthogonal, if you have an orthogonal set of vectors, multiplying those vectors by scalars won't affect the orthogonality of the set. So I'm going to leave, right, we could say or b prime. I'm going to use, now again, if you were asked on a test or something, what vectors are you getting for an orthogonal basis from the Gram-Schmidt process, these would be them with the fractions. But now that I have this orthogonal set, I can multiply these by scalars if I want to make things a little simpler. Now 0, 1, 1 is nice. I'm just going to get rid of the fractions. I can multiply this second vector by 2, get 2, 1, negative 1, and multiply this third vector by, 3 halves. All right. I mean, you can multiply by 3, get 2, negative 2, 2, but, cut those all in half. I multiply by 3 halves, you get 1, negative 1, 1. This is also an orthogonal basis. For R3. And again, you can double check, take the dot products. These two would have a dot product of 0. These two would have a dot product of 0. And these two would have a dot product of 0. Okay. And they're a lot nicer looking because they're all integer entries. But be careful, don't do that right away. Okay, don't do that right away. Because if you're, I know it wasn't a great picture, but if you remember my picture from earlier, I need the end of U3 to be under the sum of the projections, right? Directly, I need the tip of U3 to be directly above the sum of the projection vectors. So I can't just multiply. I can't multiply the projection vectors by some scalar. Right? I got to leave it the way it is. So that's why I said leave this the way it is. All right. Okay. Yeah, it's only once you're done making the orthogonal basis from Gram-Schmidt that you can then multiply vectors by scalars to make them look nicer if you want. Please know that. All right, and then for an orthonormal basis, I would just, I'll just take the nice simple ones and multiply by their norms, right? Because remember, there's only one vector of unit length with a norm of 1 that go in the directions that these vectors go in. So then normalizing, say I get b double prime equals the length of this 0, 1, 1. The norm would be the square root of 2. Remember, it's the square root of the inner product of the vector with itself, which, the inner product of this vector with itself is just 2. So 1 over the square root of 2 times 0, 1, 1 for W1, let's say. And then the norm of this vector, would be 4 plus 1 plus 1. So the square root of 6 would be the norm, so 1 divided by the square root of 6 times the vector 2, 1, negative 1. Let's say that's W2. And then the norm of this vector is the square root of 3, right? The dot product of it with itself would be 1 plus 1 plus 1, or 3. So the norm is the square root of 3, so 1 divided by the square root of 3 times the vector 1, negative 1, 1. And I'll call this W3. And this is an orthonormal basis for R3. Great. And again, let's picture it. Let's draw pictures. Again, I got you saw my 3D picture earlier. It was terrible. All right, so I'm going to go back to that GeoGebra website. Now they do have a 3D calculator attachment as well. So going back to the GeoGebra site, I got the 3D calculator brought up here. Now I've already got the vectors in. Remember U1 was 0, 1, 1, U2 was 1, 1, 0, and U3 was 1, 0, 1. And you can see, looking at this set of vectors here, that they're not orthogonal, right? I mean, they point in different directions, sure. I mean, you can just scroll around here, see that they point in 3 different directions, so they do form a basis for R3, but they're definitely not orthogonal, right? And hopefully it's clear to see from this picture. Now, remember U1, I'm going to keep U1. That was V1, right? So V1 for my orthogonal basis was 0, 1, 1. And then through that Gram-Schmidt process where I took U2 minus the projection of U2 onto V1, I got what I'm calling V2 was the vector 1, 1 half, negative 1 half. So 1, 0.5, negative 0.5. All right, do you see how that vector, right, the black one that just showed up, is perpendicular, if I get rid of these two, is perpendicular to the red one. Right. Maybe you can see it right. Let me zoom in a bit. See, maybe there, that's good, right? You can see it maybe there. They are orthogonal, they are perpendicular. Let me color this a different color. Say green. All right, and then the third vector, right, where I took U3 and then subtracted U3's projection onto V2 and V1, we got V3 was equal to the vector negative, it was 2/3, negative 2/3. I know they're rounding there to 0.67, but, and then positive 2/3 again. All right. And you see that these vectors are orthogonal, right? Like see the red and the black form a 90-degree angle. Maybe it's easy to see there. And then the red and the green would form a 90-degree angle. Maybe you can see it there. And I already showed you the green and the red. So these do form an orthogonal basis for R3, these 3 vectors. All right, and then let me punch in the unit vectors in the same direction as these, right? And that was the W1 was 1 over the square root of 2 times times the vector 0, 1, 1. Right, and you see that vector see the one in the red vector, that new one that just popped up is in the same direction as the red one, but it's a unit long. All right, so let me get rid of that red one. All right, there. And then W2 should point in the same direction as V2 as the green one, but just be a unit long. All right, so W2 should be, and I said it was 1 divided by the square root of 6 multiplied by the vector 2, 1, negative 1, negative 1, come on. And you see that one that showed up, see it's pointing in the same direction as the green, it's in line with the green here, but it's shorter, it's a unit long. All right, so let me get rid of the green one. And now, W1, W2 are perpendicular, orthogonal. I just need to, do the unit vector for V3, W3. All right, so W3 was 1 divided by the square root of 3 multiplied by the vector 1, negative 1, 1. All right, and again, it's on the same. You see those two that are on the same, the 2 arrowheads in line with each other. One of those is W3, one of those is V3. It says W3 as a unit long. I get rid of V3. There you go. All right, here is 3 vectors that form an orthonormal basis for R3. All right, they form 90-degree angles with each other. and are all a unit lawn. So it's just like they were the vectors 1, 0. The standard basis vectors just kind of shifted somewhere else. You know, it's like having 1, 0, 0, 0, 1, 0, and 0, 0, 1, but just, you know, tilted in a different direction. Wonderful. All right. All right. So that was again, that's a lot. I know. Right? And if there were 4 vectors, it would be even more tedious. And if there were 5 vectors, it'd be even more tedious. But it always produces a desirable result. It always produces an orthogonal, and then after that an orthonormal basis for the vector space you're looking at. All right, so what I have written out here is just the procedure, the Gram-Schmidt process over, you know, in any inner product space, not just R2 and R3 with the dot product, right, but for any inner product space. And it's the same procedure. All right, pardon me. So let V be an inner product space, and say B here is, you know, has the vectors u1, u2 through un, and say this set of vectors is a basis for V. Then B prime equals, you know, v1, v2 up to vn will be an orthogonal basis for V, where here's how these V vectors v1 through vn are defined. Here's how they're constructed. So remember, I just let v1 be u1. Simple. Then v2 will be u2 minus the projection of u2 onto v1. So that's the inner product of u2 with v1 divided by the inner product of v1 with v1, you know, times v1. Then v3 would be u3, right, the third vector from the original basis, minus the projection of u3 onto v1 minus the projection of u3 onto v2. Right? Now notice it's v1 and v2, not u1 and u2. Right? The projection of u3 onto v1 minus the projection of u3 onto v2. All right, and then v4, if I wrote it out, v4 would be u4 minus the projection of u4 onto v1 minus the projection of u4 onto v2 minus the projection of u4 onto v3. And then I would do the same, something similar for u5, u6, you know, if for some reason I had that many vectors. And I got, you know, dot, dot, dot here all the way up to, and then here's how the general formula works, right? You know, vn, right, any vector in this orthogonal basis is un, right, the nth vector from the original basis, minus the projection of un onto v1. Minus the projection of un onto v2, minus the projection of un onto v3, and so on, all the way up to minus the projection of un onto v sub n minus 1, right, the v vector before this, and that's the last one. All right, that is a handful there. All right, and that can be a very tedious process, but it will always result in what you desire. It will always result in an orthogonal basis for your vector space, for your inner product space. And then once I've got these v1 through vn, you simply divide each of them by their norms, and you'll have an orthonormal basis, right? And then b double prime equals, you know, w1, w2, all the way up to wn will be an orthonormal basis for V, where, you know, each of the wi's, you know, vector w sub I is just vector v sub I, one of the v guys up here, divided by its norm. Right? And remember, the norm of a vector is the square root of the inner product of that vector with itself. And this is for I equals, you know, 1 to n for all these vectors. They'll all be unit vectors and orthogonal, thus orthonormal. Great. So you see how that process extended, all right? That process of, you know, just subtracting projections over and over again. All right, so I got one final example here where we're not working in R2 or R3. but on a different inner product space, right, with a different inner product, an inner product that's not the dot product. And I'm not going to really be able to draw a picture of these or go to some website, right? So I'm just going to have to go with it, right? And we'll figure out an orthonormal basis for P2 using this Gram-Schmidt process. So my inner product space is P2. Now remember, P2, this is the set of all polynomials of degree 2 or less. Now this is one I really haven't brought up all that much, if at all. Here it is now. The inner product of two polynomials is the value of the first polynomial at 1 times the value of the second polynomial at 1 plus the value of the first polynomial at 2 times the value of the second polynomial at 2. Notice all these evaluations here. This is called the evaluation inner product on P2 at the vector 1, 2, right? So it's like, I plug in 1 to both polynomials and take their product, then I plug in 2 into both polynomials and take their product, and then add them up. So it's kind of like a dot product. You see how it's the sum of some products here, but we're doing evaluations, right? Plugging in values to polynomials and evaluating them. All right, and you can verify that this does indeed satisfy all 4 inner product axioms, right? It's symmetric and additive and homogeneous and got that positive definiteness. Okay. Now my basis B for P2 is, now remember, this is not like the dot product here. I mean, I said it's similar, but it isn't the dot product, and it isn't the standard inner product on P2. So remember how normally we would call this the standard basis for P2, right? Every polynomial of degree 2 or less is some multiple of 1 plus some multiple of x plus some multiple of x squared, right? So most people, this is usually the standard basis for P2. Not now. Not with this inner product. All right, I'm going to tell you right now, this is not, you might think, hey, wouldn't this be orthogonal since this is the standard basis? Again, normally, yes. But this is not orthogonal. Sorry, dog's barking. Sorry about that. So I'm going to show you that this particular basis, and it is a basis, it does span P2 and they're independent, but it's not an orthogonal basis under this inner product. And let me show you. So let's take the inner product of, U1 with U2 here, 1 with x. So according to this, it'd be the value, this is my P and Q. It'd be the value of the first polynomial at 1, which is 1, times the value of the second polynomial at 1, which would be 1, plus then the value of the first polynomial at 2, which is still 1, right, it's constant, times the second value of the second polynomial at 2, which is 2. And we get 1 plus 2 is 3, and that's not 0. So U1 is not orthogonal to U2, because their inner product isn't 0. Right. Now under other inner products they may be orthogonal, but under this particular inner product they are not. So that's why I keep saying, and you've heard me say it in other videos, I keep saying pay attention to how the inner product is defined. Alright, well since I can see that this is not an orthogonal set, not an orthogonal basis for P2, let's go through, use Gram-Schmidt process to find an orthogonal basis. Gram-Schmidt. Alright, so first, again, I'm trying to find an orthogonal basis, which I'll again call B prime, with three vectors again. It's P2. Every basis should have 3 vectors for P2. It's dimension 3. So I'm trying to find this orthogonal basis with vectors v1, v2, and v3. And the first one, v1, is simply the first vector in my original basis u1, so just the polynomial 1. So v1 is the polynomial 1. Okay. Second step, the second vector, v2, and I start off with the second original basis vector, right, u2, and then I subtract from that the projection of u2 onto v1, which is u1, but which is this, the inner product of u2 with v1 divided by the inner product of v1 with v1 times v1, right? This is the projection of u2 onto v1, and that's where I'm stopping. Right, there's only the 1 before it. All right, so what is this? u2 is the polynomial x minus, and then what is the, these inner products here? Now, what's the inner product of u2 with v1 or u1, which I already found, right? Remember, this is u2. u2 is x, v1 is 1. That's 3. So the numerator is 3, and the denominator, what is the inner product of v1 with v1? And again, v1 is just 1. So this is going to be 1 times 1 plus 1 times 1. 1 plus 1 is 2. The inner product of v1 with v1, using this inner product, is 2. So minus 3 halves times v1, right, times 1. So this second polynomial in the in what's going to be my orthogonal basis, right, this v2, is the polynomial x minus 3 halves. Right. So v1 is 1, v2 is x minus 3 halves. All right, now for the third vector, right, v3. So v3, again, I start off with u3, the third basis vector, then minus, and then I subtract now 2 projections. The projection of u3 onto v1, so that would be, the inner product of u3 with v1 divided by the inner product of v1 with v1 times v1, and then I also subtract the projection of u3 onto v2. So the inner product of u3 with v2 divided by the inner product of v2 with v2 times v2. All right. Okay, so let's figure out what these are. All right, u3, that's that third original basis vector, that's x squared, minus, and then what's the inner product of u3 with v1? All right, do this here. I'll find these separately. So what's the inner product of, now u3 is x squared and v1 is 1. Right, so going through the rule, the inner product is, the first polynomial at 1 times the second polynomial at 1. So it'll be 1 times 1, or 1, plus, and then the first polynomial evaluated at 2 times the second polynomial at 2. So that's 2 squared times 1, 4 times 1. 1 plus 4 is 5, right? So the numerator, this inner product of u3 with v1 is 5. And we already did the inner product of v1 with v1. I did that back here. That was 2. So it's 5 halves times v1, right? So times 1. Right? v1, again, v1 is the polynomial 1. All right, minus, and then the projection of u3 onto v2. All right, now v2 is x minus 3 halves. So I'm trying to find the inner product of u3 with v2. So x squared with x minus 3 halves. And there's u3 with v2. So going back through the rule for the inner product here, this is the product of both polynomials at 1. So that's 1 times, 1 minus 3 halves is negative half. So 1 times negative half, that'd be negative half. Plus, and then the product of the polynomials at 2. So 2 squared is 4. 2 minus 3 halves would be 1/2. 4 times a half is 2. And then negative 1/2 plus 2 is 3 halves. Alright, so the numerator, of this second projection, this subtracting the projection of u3 onto v2, the numerator is 3 halves. The denominator is, what's the inner product of v2 with v2? So what's the inner product of x minus 3 halves with x minus 3 halves? Right, that was v2 that I found earlier, right? So back to the inner product rule. So the first term is what's the value at 1 squared, right? Because of the same polynomial. Now 1 minus 3 halves is negative half, but squared would be a quarter. Plus, and then what's the value at 2 for both of these squared? And that'd be another quarter, right? 2 minus 3 halves is another half. And squared would be a quarter. A half times a half. So that's a quarter plus a quarter, that's 2 quarters, which is a half. So the denominator, this inner product of v2 with v2, is 1/2. And then this is getting multiplied by v2, and the v2 was the polynomial x minus 3 halves. And then we simplify this. Now 3 halves divided by 1/2 is just 3. Right? So I have x squared, right, that was u3, minus the projection of u3 onto v1 was just simply 5 halves, right, 5 halves times 1. Then minus the projection of u3 onto v2 would be, again, I'm distributing, this is negative 3 here, I'm distributing to x minus 3 halves. So it'd be minus 3x, and then minus 3 times, negative 3 halves would be plus 9 halves. And then combining some like terms, we're getting vector 3 here is x squared minus 3x, and then negative 5 halves plus 9 halves is plus 4 halves, or 2, plus 2. Wonderful. Okay. Now I just write this. Now I have an orthogonal basis for P2 under this evaluation inner product. Right, so the vector, B prime equals 1, right? That was v1. v2 was x minus 3 halves, and then v3 we saw was x squared minus 3x plus 2. Right, this set of polynomials is an orthogonal basis for P2. Under this inner product. Right, under this, again, the concept of orthogonal depends on the definition of the inner product. So under this inner product, this is an orthogonal basis for P2. And you can double check if you'd like. Take the inner product of these two, take the inner product of the first and the third, take the inner product of the second and the third, and you should get 0. Right, you should get 0. All right. So now I have an orthogonal basis for P2 under this inner product. Let's find an orthonormal basis, right? So I want the norms of these, right? So what's the norm? I'm going to normalize these, right? What's the norm of V1? All right, so again, that's just the norm of 1. All right, V1. Remember, this would be the square root of the inner product of V1 with itself. So we already did that earlier, right? I just have 1 times 1 plus 1 times 1 if I use 1. So that's the square root of 2. All right, so I want to multiply the first vector by the reciprocal of this, 1 over the square root of 2, to get a unit vector under this inner product. All right, and what's the norm of vector 2? Again, that's the norm of x minus 3 halves. Now I did this one earlier, right? I did the inner product of x minus 3 halves with itself. I got a half. So the norm will be the square root of a half, which that's 1 divided by the square root of 2, right? Or square root of 2 over 2. But what I'm going to do is, right, I'm going to take this and multiply by the reciprocal of this. All right, so I'll multiply the second vector by the square root of 2. Okay, and now the norm of vector 3, I do not know. That's the norm of this x squared minus 3x plus 2 polynomial. So again, this is square root of the inner product of this polynomial with itself. So what the value of this polynomial at 1 squared plus the value of this polynomial at 2 squared. So the value of this polynomial at 1 is 1 minus 3, that's negative 2, plus 2 is 0. So the value at 1 squared is 0. And the value at 2 squared would be 4 minus 6. 4 minus 6 is negative 2 plus 2. That's also 0. Okay. I may, alright. Yeah, looking like a problem here. Sorry, let me pause this for a second. Okay, so after looking into this, I just realized that I made a giant error, and I must apologize profusely. But this goes to show you, check your work before you get started. What I have found here is that the inner product, right, of x squared minus 3x plus 2 with x squared minus 3x plus 2 under this inner product is 0, right? That's not wrong. Okay, I wasn't wrong there. But, this vector is obviously not the 0 polynomial from P2. And I realize my folly. Alright, so I guess you should probably double check this as well. That would mean that the function I had in the beginning, that evaluation inner product, right, this one I had here, this does not satisfy the positive definiteness that I mentioned earlier. And again, I'm very, very sorry about that. I think where I went wrong was I actually pulled this I pulled this formula from an exercise, and I guess I just didn't read the instructions on the exercise. So read your instructions. Big lesson. The instruction on the exercise I pulled this from was verify, determine whether or not this is an inner product on P2. And it turns out it isn't. And I pulled an one of those even numbered problems from a book, so I didn't have the solution to look at right away. I didn't read the instructions in the first place. So that means that this particular formula I was given is not an inner product on P2. And everything I did for that last example is pointless. Everything I did on that last example is pointless, because this is not an inner product space. What I described up here. All right, this is not an inner product space. Okay, So I'll be sure to put a little comment in the video description to let you guys know to skip this. Now, if and this is polynomials in P2, I should have known by looking at this. There are polynomials in P2 will have two complex roots, two roots. So like if a polynomial had roots of 1 and 2, this would be 0, like x squared minus 3x plus 2 does, right? This factors to x minus 2 times x plus 1. Both of those would be 0. Well, G. So yeah, if you have so for a vector space with a certain dimension, the number of terms in the evaluation inner product needs to be at least one higher than that dimension. It looks like for polynomials at least. So let me start over. Like I said, I'll put in the description where to start the video again. I'm gonna start again, but that did let you know that hey, I make mistakes as well. It can happen, but notice how I caught it though. All right, something was wrong. I wanted those things to be unit vectors, not have a norm of 0. So all I did now, it's the same thing basically, but believe me, I actually verified this one before I restarted the video and recording. This is now the evaluation at a vector with 3 components, right? And no polynomial of degree 2 or less is going to have 3 zeros, right? So there's no polynomial where all of these is going to be 0. Right? No polynomial of degree 2 or less where all 3 of these terms are going to be 0. So I just added one more term on. So this, and again, I verified this myself. This is going to satisfy the symmetry, the additivity, homogeneity, and positive definiteness, right? The only way that the inner product, this function, a polynomial in itself will be 0 is if the polynomial is 0. Right? So p of 1 times q of 1 plus p of 2 times q of 2 plus now p of 0 times q of 0, and this satisfies an inner product. Is a properly defined inner product on P2. Again, I apologize very much, but the process I'm still going through the same process. All right. So we have our basis for P2, right, with vectors 1, x, and x squared. Again, I'll call this u1, u2, and u3. And this is not orthogonal, right? Because again, if you took the inner product of 1 with x, this would again be 1 times 1 plus 2 times 2, or sorry, 1 times 2, 1 times 2 plus 1 times 0. So I'm getting 3, right? Getting a value of 3 there, which is not 0 again, right? Not 0. So the u1 again is not orthogonal to u2 under this actual inner product, right? This is actually an inner product this time. All right, so now we go through Gram-Schmidt. It can't hurt to see these formulas again, right? Even though the first time I did them with the P2 last example was a mistake. All right, so first step, right? Again, I'm creating a new basis called B prime. That's going to be an orthogonal basis to P2 with V1, V2, and V3. All right, where the V1 is simply U1. All right, so just the polynomial 1. All right. And second, the V2 is the vector U2 from our basis, our original basis, minus the projection of U2 onto V1. Right, so the inner product of U2 with V1 divided by the inner product of V1 with itself times V1. Right. Now U2 is x minus, we already did the inner product of U2 and V1, right? That's 1 and x. That's up here, that's 3. And then the inner product of V1 with itself, this time is 1 times 1 plus 1 times 1, because V1 is just 1. So the value of all these is 1 plus 1 plus 1. So 3 again. times v1. So we're getting x minus 1. Right? X minus 1 will be the second polynomial in our orthogonal basis. And again, I promise you, this is working, or this is an actual inner product. I can't apologize enough. Okay, and then finally the third vector in our orthogonal basis. V3 is going to be, u3, so x squared, right, u3 from our original basis, then minus, 2 projections. The projection of u3 onto v1, so that would be the inner product of u3 with v1 divided by the inner product of v1 with itself times v1 minus the projection of u3 onto v2. So the inner product of u3 with v2, and v2, not u2, divided by the inner product of v2 with v2 times v2. Alright, now let's see what we get. This is x squared minus, now again I'll do these over here. What's the inner product of u3 with v1? So that's the inner product of x squared with 1. Alright, so that's 1 times 1 plus 4 times 1 plus 0 times 1. So that's 5. Alright, and then what's the inner product of, now we already did v1 with v1. v1 with v1 was 3. So 5/3, right, minus 5/3 times v1, right, times 1. I'll put a dot, right, times 1. Okay, and then the next projection, u3 with v2. Right, so what's that numerator? u3 with v2. Now u3 is again x squared, but this time, v2 we saw was x minus 1. X minus 1. Alright, so x squared with x minus 1, and the values at 1 would be 1 and 0. So we have 0 plus the values at 2 be 4 and 1, and the values at 0 would be 0 and negative 1, so 0. So we're getting 4 there. So I got 4 in the numerator, 4 in the numerator, and then what's the the inner product of v2 with itself? The inner product of v2 with itself is the inner product of x minus 1 with x minus 1. So the value of these two at 1 is both 0, so I have 0 plus the value of these two at 2 is 1. 1 times 1 is 1, and the values at 0 is negative 1, but negative 1 times negative 1 is 1, so adding those up, that's 2. Right? So I get minus 4 divided by 2 times, v2 is x minus 1. Alright, and then we distribute, combine like terms here. This is x squared minus 5/3. And then this is negative 2 I'm distributing, so minus 2x plus 2. So here's v3. v3 is x squared minus 2x, and then minus 5/3, this is plus 6/3. Right, minus 5/3 plus 6/3 is plus 1/3. Alright, so this should be good. Alright, and again, hopefully we get norms of 1, norms that we can actually divide by, not norms of 0 here, because none of these are the 0 polynomial. Alright, so this set here, so b prime equals 1 x minus 1 was v2, and x squared minus 2x plus 1/3 should be an orthonormal basis, right? Unlike the last one. An orthonormal basis for P2 under this inner product, right? Under this, under this actual inner product this time. Right. Okay, then let's find an orthonormal basis for P2 under this inner product, right? So here's, again, orthogonal basis. Now let's find their norms, right? Now again, that's V1. So what's the norm of V1? Again, that was the square root of 3. All right, because the value of 1 at 1, 2, and 0 is always 1. So this would be 1 times 1 plus 1 times 1 plus 1 times 1. That's 3. And then the square root of that. All right, and the norm of V2 be the square root. And I did the inner product of this with itself on the earlier page, right? That was 2, so the square root of 2. All right, then the norm of V3 would be equal to, when I plug in 1, gives me a square root. Plugging in 1 to V3, I get 1 minus 2 is negative 1 plus a third, would be negative 2/3. And that's being doubled, squared. So that's 4/3 plus, and then the value at 2, 4 minus 4 is 0 is a third, but then squared is a ninth. And what did I say? 4/3 is 4/9, isn't it? All right, 1, negative 1 plus 1 is negative 2/3 squared would be 4/9. I'm sorry. Man, I'm really flustered after that big mistake earlier involving the non-inner product. And then we get another ninth, right? When I plug in 0, I get a third, and then we're squaring that, so plus another ninth. So we get the square root of 6/9, or the square root of 2/3 here. All right, 6/9 or 2/3, which, if I multiply the top and bottom by the square root of 2, that'd be 2 over the square root of 6. Right? And I'm going to multiply this vector by the, and thank goodness none of these had a norm of 0. Because again, like I said, I double checked this, that this actually is an inner product up here on P2, unlike the formula I had before, which I found out way too late. All right, so now just dividing each of these by their norms, or multiplying each of these vectors in B prime by the reciprocals of their norms, we get an orthonormal basis for P2 under this inner product. So say this is B double prime. I multiply 1 by the reciprocal of the square root of 3, so that's just 1 over the square root of 3. And then x minus 1 times 1 over root 2, so 1 over root 2 times x minus 1 for the second polynomial, and then the square root of 6 over 2, or the square root of 3 halves, right, whatever the reciprocal of this, times x squared minus 2x plus 1/3. Right, this is an orthonormal basis for P2 under this actual inner product. Okay. All right, and again, you can verify that they're orthogonal. And did I put? Man, I'm making all sorts of mistakes here now. It's orthogonal up here, the 1, the x minus 1, the x squared minus 2x plus 1/3. That's an orthogonal basis for P2. And then I divided by the norms and got the orthonormal basis. And this is a rough one. Right, sorry, I went off the rails there when I had that improper inner product before, right? This is a proper inner product. And we have established our proper orthogonal and orthonormal bases. All right, so again, I'll hopefully read the descriptions, sorry, and I'll put it in a kind of a disclaimer saying, hey, there's an example there. If you want to see me make a mistake, great. Where I don't have an actual inner product and I'm still working, but I'll put in like a little a mention of the time that you can start the video at for this last better example where there's an actual inner product space. All right, So the Gram-Schmidt process, though, right? Notice I didn't change the process, even though the inner product was improper before. The process stayed the same. All right, it was this thing here. All right. So if you're going to take anything away from this video, it's the following. Right? If you have V is an inner product space and B is some basis for V, then you can construct an orthogonal basis by, say V1 through Vn. Let V1 be the first basis vector, V2 be the second basis vector, the original basis, minus the projection onto the V1. V3 equals, the third basis vector U3 minus its projection onto V1 and minus its projection onto V2. And then this just keeps going. Right? That subtraction of projections. And then for an orthonormal basis, you just take your orthogonal basis and normalize all the vectors. All right, so lots of stuff going on there. Again, I apologize one more time for the mistake with the example where the inner product I gave was not an actual inner product. Again, that teaches you the lesson to read instructions on problems before you do them. So like I said, I pulled that problem from an exercise where it was asked, to determine if this is an inner product on P2 or not, and it wasn't. Hey, so just read instructions and pay attention. Right? I keep telling you to pay attention. I didn't do it myself. It happens to the best of us. All right. So hopefully the rest of them, right, the one involving R2 and the one involving R3, and then this last example involving P2, hopefully those were informative and easy to follow. All right, lots of projections, lots of inner products here, lots of symbols to go around. And hopefully enjoy practicing problems like this. And hey, if you want to go through, if you want to not make the same mistake I did, verify that the inner product you're given is actually an inner product. All right, is it symmetrical? Does it have additivity in the first slot, homogeneity in the first slot, and is it positive definite? And where the inner product of a vector with itself is always greater than or equal to 0, but only equal to 0 if the vector you're looking at is a 0 vector, which wasn't the case in my example earlier where there was a mistake. All right, so thank you very much for watching, and one more time, I am very sorry.